Good afternoon, everybody. My name is Chris Miranda, and I'm one of the board members here on the SCTE Rocky Mountain Chapter Board. And welcome to our last Thursday event here for October. We've got a great training session in store for you guys. It's around high split HFC amplifier performance by Diana Linton from Charter. And next slide, Justin. All right, just a few intro slides from the chapter to get out of the way before we get this training going. But at the Rocky Mountain chapter, our mission is to be the best chapter in the world by enriching the lives of our members through ongoing growth, development, and connectivity. And as you can see, the awards there on the left, we've been striving for more all the time. So. SCTE membership, please make sure that you guys are active members. It's very important. And then secondly, make sure that you're associated to the chapter, because then you'll get all the email updates that we send out from the chapter. I'm sure that's how you heard of this, but we always want to make sure that people are set up correctly in their profiles. But for Comcast, if you're a Comcast employee, there's the CAP program, and those are the instructions there on the left on how to renew your membership. And for all others, there are some other CAP participants within the SCTE where the company pays for their membership, but we don't have all the details laid out there. So just check it out on scte.org. Next slide. Certifications. So definitely one of the good things that many people in the industry are striving to help make themselves look better on their resume is through certifications. And so these are recognized across all cable companies. These are, SCTE wide. So there's a way to put yourself above, some of your peers when it comes time for promotions or new job opportunities. And we also have an incentive program here at the chapter where we'll actually pay you to get certified. So we'll reimburse any of your out-of-pocket costs, but then there's also an incentive reward on top of that. So feel free to reach out if you have any questions on that. Next slide. These are the certifications that the SCTE has to offer. So many different levels of the industry. So anything from installer to network to transport head end, and then engineering levels for video, IP, and DOCSIS. Next slide. And let's connect on social media. We've got social media pages up on Facebook and Twitter, and of course there's always email, and then we have our website. And then our guest speaker here, I won't read this whole thing, but Deanna's got a lot of great experience with HFC architecture, and she's with Charter as a senior network engineer. With that, I will turn it over to Deanna. Enjoy, everybody.
Thank you, Chris. Thanks, Chris, and hello, everybody. First of all, thank you, everybody, for joining me today, and thank you, Nick, and the Rocky Mountain chapter for the opportunity to be here sharing a little bit of my knowledge. For the next 45 to 50 minutes, I'm going to be talking about the importance of RF amplifier performance characterization. I know it sounds pretty boring, but I promise I'll do my best to keep it more dynamic. And why did I get interested in this? So I am gonna share a personal story why I got involved in all this. At the end of 2020, during my first month working at Charter, two of my coworkers, Keith and Dennis, spent a ton of time getting me up to speed, teaching me all about cable, and they introduced me to amplifiers one of those days, and that caught my attention based on my background. Then, after a month or so, Esteban joined our team, and to his misfortune, he had to sit next to me. So I started asking him questions all the time ever since. One day, I was having an issue with an NPR test setup for an amplifier testing, and I, of course, went to Esteban and asked him about it, and then he asked me if I really understood how the NPR test equipment worked. That made me realize that I didn't really know much details. So he provided me some information, and also thanks to the semiconductor and amplifier vendor community, which have been a great support for me. All the material they gave me started the journey for me on learning everything I know about amplifiers. Also, thanks to Ron with all his papers because they brought me up to speed pretty quick. For today, I will be explaining a bit of the amplifier background on the two-way amplifier evolution, also some of the configurations that have been used for the whole cable industry history, why RF performance characterization is so important. Then we're going to talk about RF performance characterization metrics, and then we're going to focus on one of those metrics, which is NPR or noise power ratio. Then we're going to go to the NPR setup, the dynamic range plot, which is the result of the NPR testing, how we use NPR today, the future NPR, and some final conclusions. Can we go to the next? On the overview, this is just an schematic, basic schematic of an amplifier. These amplifiers are stations that are or devices that have two paths, one forward and one reverse. The forward is the blue part of the diagram, and the orange is the reverse. Both of these paths are typically contain different passive elements like equalizers, paths, directional couplers, and diplexers. And the signal travels on the forward from left to right, passing through a filter that captures the high part of the spectrum and goes to different adjustments like slope and padding before it goes to the main stage or gain block. Then depends on the type of amplifier, if it goes straight to the output port after the filtering, or it gets split and goes to different other output ports. On the reverse, the signal travels from right to left and goes through the orange path, and the lower part of the spectrum is filtered, then goes to a slope and attenuation control, and then to the gain stage, and then out to the left to the next station. These devices are an essential component in defining the capacity and broadband performance of HFC networks by allowing multiple signals to carry over coax cable with minimal degradation. Amplifiers have different names based on performance specifications and network location, and also the type of architecture. So some of those are express, bridger, and line standard amplifiers. But regardless of the type of amplifier, all of them must perform bidirectional amplification of signals without adding much degradation. The motivation of operators to offer highly competitive service has driven the migration to all digital networks, allowing cable operators to support higher frequencies and wider bandwidths. This has driven the development of high-capacity complex broadband amplifiers throughout the years to support expanded operating bandwidths. Next one. I tried to compile the history of the technologies used on the amplifiers on the forward and how the bandwidth has been increasing throughout the years. So on the forward, for those that had that were able to work with the legacy equipment, those first generation of hybrid amplifiers use a technology called discrete silicon bipolar junction transistors, or BGT. And in those early deployments, there was a limited number of analog channels. The performance of these hybrids incorporating silicon BGTs met the network requirements at that time, since amplification was only required across a 450, then 550, up to 750 megahertz. They were sufficient to provide cable operators with the performance needed at the time. Then in the early 1990s, gallium arsenate gas-based dye products were introduced on early prototypes of 860 megahertz amplifiers. At first, this technology of hybrids demonstrated questionable performance versus the best BGT hybrids of the time. But as the semiconductor manufacturers improved the gas dyes, and during the early 2000s, these hybrids were implemented and outperformed the BGT hybrids. They improved bandwidth up to 1 gigahertz and performance measurements, including multi-carrier distortion, RF output power, and power efficiency. The next generation of hybrid amplifiers was introduced around 2008 when gallium nitride GaN dye was adopted by the cable industry. The introduction of power doublers, gain blocks, providing higher power at higher frequency with better efficiency and performance, and also were able to stand higher temperatures. The GaN-based amplifiers match the performance of the gas or can be slightly better with lower power consumption, which is great for the cable industry, providing higher output powers. The distortion and better distortion and performance. This technology has been implemented mostly in beyond 1 and 1.2 gigahertz amplifiers and will be implemented on future 1.8 gigahertz amplifiers. As we increase the bandwidth, we need to operate amplifiers at higher frequencies, and we need to be real cognizant of the amplifier TCP limitations. Since, as we see on this graph, we are reaching the limits of the hybrid or semiconductor devices for unexpected performance. Since we're pushing the limits of the semiconductor technology, we're working pretty close to the compression region. That's why we need to be mindful of the operation of these amplifiers. For the 1.2 and for the future 1.8, we need to be real careful of following design prints to avoid operation of amplifiers in the crashing region. So as we can see, as we go higher in frequency and wider in bandwidth, the TCP limits are getting very close to what the operation is. Next one. On the reverse, there is not a lot to say really because the evolution has been marked by the forward. And so far, we're just introducing the high split, which goes to 204. And then when the introduction of DOCSIS 4.0, the ultra high split will be implemented in the future, supporting a return bandwidth up to 684 megahertz. But for now, we're just gonna let's focus on high split. Next one. Here, I just wanted to capture like the evolution of how simplifying the amplifier, trying to capture the technologies used on the hybrid amplifiers as we know them today. So for those legacy amplifiers, back in the 1970s, when the first standard package and hybrid circuitry for cable television systems was introduced, it was known as hybrid or SOT. The amplifiers operating in a really narrow band and did not need the use of that many gain stages. So the technology on the forward path for some of the early hybrids, they only needed one of them, and it was a push-pull stage. That was sufficient to meet the specs of and be able to carry the bandwidth throughout the coax cable. For a brief period of time, 450 and 550 amplifiers included a feed-forward stage. It was briefly because this technology had some limitations, bandwidth limitations, and they never developed beyond that bandwidth. Then, as bandwidth increased and performance requirements were tighter, the push-pull circuits evolved to a parallel hybrid, which is two push-pulls in parallel. And this game block introduced improvements on distortion performance and provided higher power levels. The output stage today that we know as a doubler uses a driver, is a doubler, and it has mostly GaN technology, providing higher performance and higher output levels. And since we're keeping pushing the limits on bandwidth and power levels to overcome coax attenuation and avoid respacing amplifiers, we are using a driver stage to help that doubler output stage. On the return, the bandwidth, the configuration has not changed as much because the bandwidth has been increasing at a lower scale. And so we don't need as many blocks as on the forward. Next. So now let's talk about why RF characterization performance is so crucial. It will help us to understand the amplifier TCP limitations for unexpected performance, first of all. Second, it will help us make educated design decisions around the HFC network evolution. And third, it will help us to properly operate the amplifiers to deliver quality signals throughout the HFC network. Next. How we measure RF amplifier performance characterization? Well, first, amplifiers are not perfectly linear. So this means that if we plot the output voltage versus the input voltage in an amplifier, we won't see a straight line. There are non-linearities introduced by the semiconductors using the gain blocks that we discussed already, and there are effects that are introducing non-linearities due to saturation effect of the amplifier operating close to the crash region, especially for the 1 gig and up amplifiers. When modulated signals pass through the amplifier, signals are subject to distortion, and as a result, products or intermodulation products are generated. They do look like noise-like band energy for now because we're using modulated signals. That is why currently amplifier developers and cable operators use various metrics to evaluate digital signal quality through the amplifier, including but not limited to carrier to thermal noise, carrier to composite noise, carrier to intermodulation noise, bit error rate, and modulation error ratio. This will help us not only understand the RF amplifier performance, but it will help us also to understand how to operate it and to not crash it and have issues in the field. Next. Another metric is NPR, and that's the metric we're going to be focusing on today. And the reason why is because as the number of digital signals increases, the input level profile and the distortions exhibit noise-like characteristics. That's why NPR or noise power ratio might be a better metric to measure those intermodulation distortions and capture those accumulation distortions from the test signals that we're inputting to the amplifier, helping us understand the limitations on total composite power. Next one. So to better understand NPR, we can use this graph because NPR, in a few words, how quiet an unused channel in a multi-channel wideband system is based on random activity on the other channels. So from this graph, we can see that as the orange input signal increases, the output signal increases through the amplifier. When we notch one of those channels, we see as the input signal and the output signal increase, the thermal noise plus the intermodulation products on the notch start increasing as well. So the main cause of this is that the performance is affected by that. Next one. On this one, I just did a really simplified version of a setup. And then if anybody's interested, you should check the NPR SCTE test setup for all the details. But here the message is that the input signal is generated. It could be a modulated signal or injected noise, white noise, and it goes across the amplifier bandpass. Then that signal goes through a notch filter in order to remove the channel that we want to evaluate. Then the position B of the switch is selected and the notch signal is fed to the amplifier, and is amplified and goes to the spectrum analyzer. Then we capture or we record the noise level at the center of the notch. Then we position the switch to A, and the input signal goes straight to the amplifier, and then to the output signal goes straight to the spectrum analyzer. The signal level at the same frequency is measured, and then we calculate NPR by subtracting the total signal power accumulated from the accumulated noise power. And then that's how visually here we see the comparison of the input signal in orange and the output signal with the noise capturing the intermodulation and noise. That's a ratio, and does help us visualize the RF performance on the amplifier at different frequencies. Next. The result of NPR is something called dynamic range plot, and this plot represents the RF output profile at one or any frequencies of interest for an amplifier across a range of input levels. From the NPR plots, we can identify these regions. The first one is called the noise region on the left, and is in this curve, as we increase the input level, the output level increases in a ratio of 1:1. This is where the power in the notch is dominated by thermal noise. The second region, as we get to the top of the curve, is the intermodulation region. And as the top of the curve is reached, the NPR starts to round. This area is where the notch is dominated by intermodulation noise. For amplifiers with amazing performance or exceptional performance, this area is really minimum. Then the clipping region, where we don't want to operate amplifiers, is at the maximum output TCP levels, and is when the amplifier is driven into saturation. In this case, the notch is ruled by the high order modulation noise. And then in this part of the curve, the NPR values decrease quickly as the input levels increase. The peak NPR is the highest NPR value in the curve, and then the dynamic range is selected based on a target NPR. For example, in the return, a more dynamic range is needed or is important because we need to have enough margin for the return amplifier to tolerate any additional energy before going into compression. We need to leave some margin for ingress, impulse noise, and any other kind of noise. That's why we need a little bit more margin. On the other hand, on the forward, as I mentioned before, we're operating the amplifiers really close to the clipping region in order to get as much performance. This is why we need to be mindful of those levels and follow the design specifications to avoid any problems operating the amplifier in the clipping zone. Next. Here, I'm just showing an example of two different NPR curves for two different amplifiers. They vary by manufacturer, but the message here is that the RF performance characterization using NPR provides us the ability to determine accurately the boundary between the linear and nonlinear or the clipping operation regions. This gives us the ability to select the optimal input levels where we can operate the amplifier distortion free. So on the left, for example, we have a target NPR in blue of 40 dB, which gives us a wide dynamic range of 38 dB. On the right, someone else can think that an NPR of 50 is better suitable for their network, so they have a dynamic range of 22 dB. And someone else can say, no, we need better performance, so we need a target NPR of 55 dB, and have a dynamic range that is less but enough to support the energy that they are expecting to get. It depends on the conditions on the plants, and it varies by the performance based by manufacturer, and the target NPR will be selected based on the network conditions. So for some, 7 dB might be enough. For others, 14 dB is better. Let's see, sorry. And in the case of the forward path target NPR selection, since we're working on to get better performance, it's okay to have a less dynamic range. But on the upstream, it's crucial to have a more dynamic range for that excess energy or ingress tolerance. In the case of, for example, optical equipment, this is really, really important because if we target an NPR that get us really close to the crashing point, then we will experience some clipping of the laser. Next one. So I put some slides to visualize better what it will mean to work on the different zones or regions. So if we work on the noise region, which is dominated by the thermal noise, in the forward, we need to be careful because we don't want to be operating with low levels on the amplifier and sacrifice performance. On the reverse, towards the end of the zone or the edge of the noise region is okay because we want to be a little bit more conservative to get a better dynamic range. Next one. On the intermodulation region, in the forward, yes, we need to work there and be mindful that we have just a tiny bit of a dynamic range. In the reverse, we are pushing it, so we're way too close, and so we have less tolerance for any ingress or any noise. Next. And then here for forward or upstream, downstream or upstream, working on the clipping region or operating the amplifier there is the danger zone. We don't want to have any compromise. We'll be compromising performance either way. Next. So the future of NPR, we have been using NPR for a long time, and as we mentioned before, it mostly has been used in the upstream, but there is a lot of potential to use it on the downstream because as we increase bandwidth and the intermodulation products are increasing as well, we have a better characterization of the amplifier. This will also, with other traditional measurements, we're limited based on the source or different elements. So this NPR will help us determine RF performance through an octave and give us a full picture. So I wrote an article back in the spring of this year, and if there is more details, I put the link there, and I'm happy to discuss any questions if there is any questions about that. But next. So I guess to close this, I just wanted to say that NPR is a metric that works better over wider bandwidths and can provide higher dynamic range than traditional MER measurements. And new testing for the future 1.8 amplifiers is showing that there is a strong correlation between NPR curves and traditional MER and BR measurements. However, I just want to make sure that MER will continue to remain a metric to measure performance in live operation environments. Cable operations will continue to use MER on the downstream and the upstream to characterize and leverage the cable modem signal. And this will help us get a sense of the health of the signals in the plant and the premises network. And I think that's all I got for today. I think I went pretty quick over that. So I think there's some questions I saw in the chat.
There are. So the first question is, what is the bandwidth of the notch used for downstream NPR testing?
The notch will depend on you can control the notch, but it has to be at least 10% of the bandwidth that you're measuring. And then, but it could be variable. And for the downstream, we will need to characterize the whole bandwidth, we will need to use a lot of notches.
Okay, thank you very much. The next question, how do NPR results correlate with MER and BER characterization in downstream amplifier testing?
Yeah, so on the testing that we have performed on the 1.8 amplifiers, or the preliminary testing that we're seeing from the prototypes, is that as we increase, if you put the three plots together, as you increase the NPR curve on the noise region, they all match. On the intermodulation region is where the big difference is, because with MER measurements we're limited by the source, but with NPR we have more visibility over higher input values, and we're not limited by the source, because right now the source will give us a maximum MER of 50 to 52, and as they evolve, so there is a straight line and in the intermodulation area. But with the NPR, you could see the amplifier is still performing okay, and it goes up. And then when it gets to a crashing point, the plot, NPR plot region and the MER plot line up on how the amplifier is crashing. MER and NPR start correlating again there. And also in the VR measurements, you could see how VR starts increasing as the crashing point it's developed.
Thank you. We have another question. Do you use multiple notches across wide bandwidth downstream measurements, especially up to 1.8 gigahertz, or is one notch enough?
No, yeah, is we will have to use different notches because performance or let's say distortions will add really different across the frequency. So we noticed that below 1.2, they add noise like 10 log. But as we go higher in frequency, it goes 14, 16, even 19 log. So we will need different notches at different frequencies, especially at the higher frequencies to really characterize the performance.
Thank you. And I believe there's going to be, oh, there it is. How many gain stages are enough for forward 1.8 gigahertz? What about return?
Yeah, on the upstream, let's start with upstream because it's easier. I think we're gonna have, depends on the ultra high split that we use. Let's say the worst case of 684, one, one to two stages will be enough. On the upstream, on the downstream, that's a different story, but we are probably gonna be ending up with three to four stages at a minimum.
And the next question, with such a high TCP, will the hybrids heat up and require additional cooling? And then in addition to that, will amplifier housing need double the count of cooling fins?
No, that's something interesting. A great question, but that's something we evaluated with the semiconductor and the amplifier vendors for a while because at first, the first prototypes of hybrids were 34 volts and they require a lot of power. And since we're going to be using a lot of stages, for multi-port amplifiers, we're like, no, there's no way we can fit those there. But the semiconductor industry came up with a second type, which is 24 volts, which are the ones that are used on the 1.2 as well. And those have high efficiency and better linearity than the ones we saw before. Also, we can accommodate those in the existing housings, even for the triple or the mini bridgers with multiple ports. Also, there is an interesting fact that now we are not just tied to the SOT package or hybrid package. There is other options like the DFN package, dual, I forgot the whole acronym, but this one provides also some new things on thermal management that and space. And since we're going up in frequency, we're able to use smaller devices, which are able to dissipate the heat on the existing houses just fine.
Oh, that's awesome. So, Deanna, are you saying that it's possible to drop 1.8 gigahertz amplifiers in without respacing?
Yeah, yeah, we're offering on the first prototypes we're seeing really high gains and it's gonna need really little spacing as far as we're seeing, but Keith in my team will be able to provide more details on that probably. But it's looking really promising.
Ah, cool. Are 1.8 gigahertz amplifiers still using Class A silicon? And is there any use of, say, Class AB with pre-distortions to help performance?
Yes, I don't think there's on that part the pre-distortion has improved a lot as well. The um, the semiconductors have implemented in the hybrids and the DFN packages or PAs a lot of pre-distortion improvements, changing ferrites, also the layout of the board. The challenge is that TCP management, which before wasn't a big challenge in the industry.
Can Operators keep running at 60 volts for their power supplies with 1.8 gigahertz amplifiers. Is there a benefit if I move to 90 volts AC?
On that part, yes, it will be better to work at 90 volts, but for the amplifier, as far as it has enough power it could work efficiently either way.
If one of the operators begins to purchase 1.8 gigahertz amplifiers, but only half load the spectrum bandwidth, will it make the amplifier unstable?
No, no, the amplifier will just operate fine. There are other limitations on having less load because it depends on the implementation of the amplifier if the losses of the equalizer and attenuators are going to be higher at the lower legacy frequencies. So that's one of the challenges that will be, but as far as stable, it will work just fine.
Any other questions? Oh, here's one. What about AGC operation? Is thermal or AGC an option? Will one be better than the other?
I feel like at that point we should just go with AGC or ASLC to make sure that since we are such a high band, like higher bandwidth, that we have better control and performance over temperature. Especially because we're gonna be impacted by coax loss attenuation by a lot.
So what other questions does the group have? Enter them in chat, please. Last call for questions. Perfect. So you're just getting a lot of allocates that are coming in, but no questions. Justin, are you closing us out? Oh, wait, okay, here's another one. Hang on, here's another one. Is NPR only used in lab environments, or will it be used in field deployments such as CMTSs?
No, yeah, we'll keep it in lab environments and we'll just make sure that the field operation understands the limitations of what we can see for the amplifiers.
Thank you. Okay, back to Justin.
Oh, sure. I guess if that's it, no more questions. Great job, Diana.
Thank you.
Hope everyone has a great rest of their day, and this concludes our webinar.
Thank you. Bye.